In this video, I'm going to be talking about another approach for event extraction. And this article is a relatively old article, but it's very important because we are generalizing the biomedical event extraction. So in this paper in 2011, they present a system for extracting biomedical events, detailed description of biomolecular interactions from research articles. This system was developed for BioNLP 11 shared task that I explained, and this task which I explained in the previous lecture. It uses support vector machines to first detect event-defining words followed by detection of their relationships. The theme of the BioNLP 11 is generalization, extending event extraction to varied biomedical domains. Our current system successfully predicts events for every domain case introduced in the BioNLP 11, being the only system to participate in all 8 tasks and all their subtasks. So this is an event extraction. In most tasks, name entities are given. Sentences are parsed. Here in B, they are parsed to produce a dependency parse. And entities not given are predicted through trigger detection in C. And in edge detection predicts event argument between the entities. And finally, event modality is predicted in F. So when the graph is converted to the shared task format, site arguments are paired with core arguments that have the same target protein. So we do parsing, trigger detection, edge detection, then unmerging, then speculation and negation detection. And this shows a site argument representation because these site arguments add detail to core arguments. Most of BioNLP 11 shared tasks define task-specific annotation terminology, but largely follow the BioNLP 9 definition of events. Some new annotation schemes, such as the bracket notation in the CO task, can be viewed simply as alternative representations of arguments. The major new feature is relations or triggerless events. Some event arguments have a matching site argument that determines the part of the protein the argument refers to. So applicable combinations of these features are then used by trigger detection, edge detection, and unmerging steps of event extraction system. For example, token features can be generated for each word token, and they define the text of the token, its pointer stem, its pen tree bank, part of a speech tag. And so sentence features define the number of name entities in the sentence as well as bag of words, counts for all words. And dependency chains follow the syntactic dependencies up to a depth of 3, starting from a token of interest. Dependency path n-grams are built from the shortest undirected path of tokens and dependencies linking together two entities. So these are feature groups that I'm talking, and one of them, for example, is trigger feature, can be built in cases where triggers are already present. Another one is external features, which are additional features based on data external to the corpus. Most tasks evaluate trigger detection using approximate span to detecting a single token, So detecting a single token is enough. And when optimizing the SVM-C parameter for trigger and edge detection, it is optimized in isolation, maximizing the F score for that classification task. So edge detection, but in the unmerging, events are defined through their trigger words, resulting in overlapping node for overlapping events. The trigger detector can, however, predict a maximum of one trigger node per type for each token. When edges are predicted between these nodes, the result is a merge graph where overlapping events are merged into a single node and its set of outgoing edges. And the Genia task is the direct continuation of BioNLP 9. And BioNLP 9 corpus consists only of abstracts. For example, in Genia 9, we have around 8,000 sentences, and it has 38% of them are nested events, which are very complex events. So we have developed a system that addresses all tasks and subtasks in BioNLP 11.